Welcome to the Earth Science Classroom. We are back looking at the Earth's interior, looking at the inner core. This is the video number 2 for the inner core. In the first video, we looked at what's on the left here, the Gutenberg and Lehmann discontinuity, the change in P wave velocity, the discovery of the refracted P wave velocity through the outer core as it increased in velocity towards the bottom of the outer core, at the outer core inner core boundary, which then Lehmann discovered and suggested that there was a solid inner core because of the P wave behavior and velocity. And then that led to more discoveries in the density composition of iron nickel alloy, about 90% iron, about 5 to 10% nickel, and then the different characteristics that basically blow you away of the temperature and pressure and depth and all that good stuff, which is awesome kind of geophysics right there. But now we're going to look at the origin of the inner core, how it came to be. And pretty much it was kind of like the Earth was basically just being being created, or maybe that's the wrong word to use, but being formed. And you have this, 4.6 billion years ago, you have this mass of molten rock and different rocky bodies in the inner planetary area around the sun, just starting to form and accumulate and grow in mass, and then mass turns to gravity, and that would be a positive feedback loop and bring in more rocky materials from the asteroid belt, that kind of thing, into the Earth to kind of like build the planet. And as it was first forming, you had the heavier elements. The heavier elements started to sink towards the center of this planetary mass, this early Earth, and the lighter elements would move towards the surface, towards the upper mantle and the actual crust. But back in those days, it was more of a molten ball that was still extremely hot and extremely new, and there wasn't any kind of differentiated layers at that point. It was just more of a sorting themselves out based on density, where they should go, and the heavier iron and nickel sank to the center of that mass where gravity is pulling, the force of attraction, and the liquid homogeneous Earth kind of cooled, and the iron crystallized. Now, this is a slow process, but it crystallized and created our solid inner core. Now, in doing that, in the crystallization process, it releases heat. It releases heat, and you start to get the different thermodynamic processes occurring within the interior Earth, which would be our conduction and our convection, which we see today in our current outer core with the motion of the liquid iron alloy and the nickel and the sulfur, thus creating a EM field, and that is discussed in different videos on this playlist on this channel. So check that out. They're pretty cool. So the heat is a big thing to discuss, because obviously our Earth is not a liquid ball that's flying around the sun. It is pretty much solid, of different densities. However, the temperature does increase, where, as I said before, the temperature in the inner core is around 6,000 to 6,700 degrees Celsius. So it's extremely hot. However, the intense pressure in PSI, or any kind of pressure units you want to use, the intense pressure creates this solid material. It's too much pressure for the rock to melt. It doesn't have enough space or volume to melt into, so it stays solid. So talking about heat, and sources of the heat. So where does, oh, that's not right. So where does the heat come from? So the first one was planetary accretion. Now, accretion means to add, addition. So the add-in of rock, the smashing together of friction, the process of forming our early Earth 4.6 billion years ago created that heat, and it was kind of trapped in there from the formation. And slowly but surely, the heat is being released. The next thing we look at is radioactive decay. Now, there are particular elements in our Earth's composition that are distributed throughout the layers, mostly in the lower mantle and the core, is the unstable isotopes that are going to break down and decay and release, alpha and beta um, uh, molecules, atoms, and this releases heat, a lot of heat, or thermal energy. When I say heat, it's just a version, a type of energy. So it's thermal energy. And you could be as detailed as you want in terms of the physics, whether you have students that have physics background or not, or chemistry background or not. But you can go as deep as you want into the physics if you want with that and the wavelengths and different spectrums. So the heat is released from decay of these isotopes, and the most common is uranium, thorium, potassium. Those are the three main ones that we look at. And if you go into engineering or physics, you'd look at uranium 235, 238 in terms of nuclear power generation, and dating of carbon dating, carbon 14, and the decay of atoms based on a certain half-life time. So it's pretty consistent. So you can use that as a way to date rocks, fossils, that kind of thing. So those are the two main ways to heat. And as I said before, the third one up here was when the iron crystallizes inside the inner core. Now this is still happening. So the inner core is actually going to grow in volume. It will stay extremely heavy and the mass will increase. So as the volume increases, so will the mass. So it'll start, right, currently it's at 33% mass and the volume's at 16.4%, and that's going to increase. So the mass will and the volume will increase as the inner core starts to enlarge and more of the outer core, the iron in the outer core starts to crystallize and turn to solid. That will release more heat. And the inner core is very slowly cooling down. Now, the implications for that are just, estimations or guesses, but if the inner core grows bigger in volume and therefore mass, then the outer core is going to, in theory, be smaller, and there'll be less convection, and therefore there'll be less movement of the iron alloy, a metallic alloy. Therefore, our EM field would, in theory, break down. And at that point, it would allow all the radiation from the sun to bombard us. And at that point, our surface systems will then start to break down very quickly. Water would evaporate, ecosystems break down, soil will become unable to use, intense solar flares would cook the planet basically. So it's a very bad situation, but hopefully that's not for another few billion years in our future. And also the sun's going to enlarge to a red giant as well, which is not good for our surface too much. So the three main sources of heat: planetary accretion, decay of isotopes and the iron inside crystallizing and the inner core expanding and at the same time cooling down. So as with all the different interior layers, there's videos on each layer, but the inner core is an awesome thing to study in terms of the origins of our planet and how it formed the outer core. And basically, we're still discovering things about it every year. And hope you enjoyed the video. Hope you can discuss it with your students. And this could be just inspiration for different activities you can do in the classroom. And if you like the video, please subscribe and leave a comment, and that'd be great. Thanks.